Hello everyone, welcome to today's video. In this video, we're gonna talk about state machines. State machines are a mathematical model of computation, and it's an abstract machine that can be exactly one of the finite number of states at any given time. So the mathematical formula for a state machine look like here. So we have a tuple of 5, and each tuple representing an group of values. So this symbol here, sigma, represent the alphabet, and this represent the states that we define or our system has. This represent the beginning state, and this is the transitions, and this value represent the states that the system will be there, and we considering the values in this set as a final state of the state machines. So let's take a look at the alphabet. The alphabet can be defined by different type of representation and or based on our need. So an alphabet can be just a number like 0 or 1, can be an alphabet A or B, or can be a combination of the numbers, alphabet, and symbols. The states set is a number of states that we define for a system, and it cannot be empty set. So this is very important. And the transition is a function that takes a state, takes an alphabet, and returns us a new state that the system will go to. In non-deterministic automaton or non-deterministic state machines, the transitions is a power set of the states and the alphabets. And finally, the finite state set is the sets that the system will be considering in this state as a done or finish when we reach to these states. So we reached our destination when we reach in these states. I have here an non-deterministic representation of a state machine, and in this state machine we are having like 5 states, and 2 of them is a finite state, and 3 of them are normal states, and state S0 is our initial state. When we want to mark our initial state or say which state the state machine begins, we're using this symbol here to say that the system begins from here. And then we draw a transition, and over a transition we can say this transition has this alphabet. So whenever we are in this state and we get this alphabet, we will go to this new state. So as you see here, I have a table, and in this table I have alphabet, and I have my all states, and now I can calculate my transition function using this table. So let's see that what we have here. If we pass 0 to a state machine and then 1, we will reach a final state. If we pass an A and 1, we will reach a final state. We can pass 0, 1, and B, we will stay in the final state, and A, 1, B, we will also be in a final state. So these are the words that our state machine accepts. So there are the accepting states that our state machine can go to. And I have here the alphabet for my state machine. I have my states. I have my transition function. And also I have here finite states that the system can have. So let's take a look at this transition state and how we can complete the values here. So we say that we are in a state 0 and we get a 0, we will go to a state 1. If we get 1, we don't know where to go. So let's put a blank here. A, we will go to state 2, and B also unknown. And we will repeat this for all other states. So when we are in state 1, with 0, we don't know, with 1, state 3, and with A, we don't know, with B, we don't know. State 2, same as state 1, and state 3, for 0, we don't know, for 1, we don't know, for A, we don't know, for B, we go to state 4, and for state 4, it's the same as state 3. So now we have completed our transition function for our non-deterministic automaton. But is there any way that we change a non-deterministic automaton to the deterministic automaton? The answer is that yes, but it depends. Converting a non-deterministic automaton to the deterministic automaton is a NP problem. So there might be a solution, but there is no guarantee that we can find a solution for this problem. And for a small example that we have here, we can actually build a deterministic automaton. So what we're going to do is that we will create the same table as before. And what we're going to do is that we're going to build a set of our state that can be reached possibly throughout our transitions for each state. So what we're going to do is we're going to say that, okay, for state 0, I can reach state 1, and I can reach state 2, and these are unknown values. I will replace them with the new state R, state reject. And I will continue this process for all other states. So basically all other values for the unknown states that I don't know where to go, I will put in a new state and I will define this state as a rejected state. So and for state 1 we have state 3, the rest is rejected. For state 2 it's the same. And here is also same as before. So what I'm gonna do now is that to draw you a new state machine which tells me a deterministic, which gives me a deterministic state machine. So I know exactly where to go when an alphabet comes. So as before, I know where to go when I get a 0, and I know where to go when I get an A, but whenever I get any other value like 1 or B, I will go to my new state that I defined. For these two states, I exactly know where to go when I have value 1. And remember, for finite states, we put 2 circles. This is a convention, and in different textbooks it can be different, but we're gonna use this notation for finite states and this notation for initial states. And as we did for state 0, we're gonna add the for 0 for A and B, 0 A B, 0 A B, and now for each alphabet we have an output for a state. So basically a deterministic state machine is a state machine that for each alphabet has an exiting edge. So whenever we have for our alphabet an exiting edge, we have a deterministic state machine. So for example, for state 0, for 0 and A, we have exiting edges, and also either for the 1 or B, we have also an exiting edge. So we know where to go when these values appear in our word. So imagine that you have a word, and this word belongs to our alphabet set, and for instance 1 0 A B C, and we feed this let's say word or input to our state machine, and whenever our state machine goes from this value to an accepting finite state to accepting state, we say that this word is accepted. Other than that, our state machine will reject the word. So this is how, for instance, text searching engines, for instance, works. They use this regular expression, which I am showing you here. This is a regular expression. So they take this regular expression, and based on this regular expression, they search inside the text to see the patterns. And whenever the patterns happen, they say, okay, this is accepting, so we found something. Whenever it's not happening anywhere, they say that, okay, we didn't find any input which which goes to the accepting state, so we couldn't find a result for input. Let's continue and finish this drawing. And from state 3 we have B. Go to state 4, and as before, for other values we can only go to a rejected SR, and when we are in SR we cannot go anywhere else. So we are here, so we have 0 1 and A, and 0 1 and A. And another thing that we can do now is that we can merge these two states together, and this basically simplifies our state machine. So we can also simplify our state machine whenever it's possible. So we just can simply erase this part and say that like this. Now we know a little bit about state machines. Let's take a look at our example. So in our example, we have a robot, and the robot can be each in a state and each given time. So we will define a state machine for a robot, and this state machine basically represent the behavior of robot. Behavior of a system is modeled as a state machine. So this is another way for a modeling. In last video we talked about the UML diagram, and UML diagram was a way to model the data types and data models and basically abstract. It was an abstraction level that we could say that what we're gonna need for programmings during the program is what kind of instances, for instance, we need, what kind of data models we need to use to be able to access the information much more convenient, with a less effort, and in a clean way and in a robust way. And now when we are talking about this modeling, we're modeling the state machine, and this state machine need also be programmed separately. But for now, we are just sticking to the definition of how the model should be, and then later we will take a look at the tools that help us to program this part too. So for now, we just concentrate on what kind of the state machine we need, and then later I will introduce you to tools like Papyrus and also Spring state machine framework, which these tools help us to realize this model. So the Papyrus is basically used for the modeling itself. The Spring state machine framework is used to convert this model to a piece of usable code. So basically, the Papyrus itself doesn't extract the code for us. We need to explicitly program the state machine, but the Spring tools help us to define the methods and all other mechanism inside the state machine much more convenient, in a much more convenient and safer ways, let's say. So take a look at the model that we defined. So a robot will start from the ideal state, and whenever a signal or event like move comes in, it will go to a new state forward. And in a state forward, whenever it gets a blocking signal, it will go to the turn state. And the turn state itself is a super state, and it has some substates inside. So basically a box here is our super state, and inside there are the substates which lives inside the super state. So if this substate is a robot state, this is a super state, and this substate inside defines what's happened inside the super state. Why is it important? Because there are lots of other states inside the super state which can be can have a transition to a new state, and this new state has the same event for all of them. So we simplify, instead of dragging a line from each state to this new state here, we just simplify. We put all those states which are using this same transition in one super state, and then simply we say that this super state, when it gets this event, will goes to the new state stop. And also this about the turn state, we have here a super state, and this super state has a substate inside. And whenever after inside the superset everything's finished, it will gives us a new signal turn, and we will go to the reset, and we will do something in this state, and then we will send a new event outside reset, and we will go back to the ideally and wait for a new signal move. So this is somehow a behavior of a robot in each given time. So we expect that the robot will be in each of these states during the time the program is executing. And inside the turn, we also have ideal state. It will get this event. As if you see, the events comes to this super state is exactly the same event that we're gonna use inside this super state, and this event will trigger a transition from the ideally to a orientation, and inside the orientation we will take care of some stuff, and then we will go to new state with the calibrate event to the reset, and then we will say we have finished our process. We'll send out the turn, and this signal will trigger a new transition here outside to go to the reset. So I will show you very quick what you should expect for our next video next week. So basically I will show you in the next video how to install a Papyrus on your Eclipse IDE. It's a plugin that you can use. Also, there is an integrated Eclipse with a Papyrus available for download. If you are already using Eclipse and you don't have or you don't want to migrate to a new Eclipse, you can simply add the plugin to your computer and use it to the model. The result of the model is this given file, this UML file, and you can use this UML file to inside your program to initiate an instance of this model as a state machine, and these are the functionalities that the Spring Frameworks gives you. We will also talk about them in next video. Thank you for watching this video. I wish that you enjoyed this video. Please do not forget to share and subscribe to my YouTube channel, and we will see each other in the next video. Thank you.